NeoBERT, a next-generation BERT. Abstract. Recent innovations in architecture, pre-training, and fine-tuning have led to the remarkable in-context learning and reasoning abilities of large autoregressive language models such as Llama and DeepSeek. In contrast, encoders like BERT and RoBERTa have not seen the same level of progress despite being foundational for many downstream NLP applications. To bridge this gap, we introduce NeoBERT, a next-generation encoder that redefines the capabilities of bidirectional models by integrating state-of-the-art advancements in architecture, modern data, and optimized pre-training methodologies. NeoBERT is designed for seamless adoption. It serves as a plug-and-play replacement for existing base models, relies on an optimal depth-to-width ratio, and leverages an extended context length of 4,096 tokens. Despite its compact 250M parameter footprint, it achieves state-of-the-art results on the massive MTB benchmark, outperforming BERT subscript large, RoBERTa subscript large, NeoBERT, and modern BERT under identical fine-tuning conditions. In addition, we rigorously evaluate the impact of each modification on GLUE and design a uniform fine-tuning and evaluation framework for MTB. We release all code, data, checkpoints, and training scripts to accelerate research and real-world adoption. 1 to the power 2. 1 Introduction. Autoregressive language models have made tremendous progress since the introduction of GPT, Radford et al. 2018, and modern large language models, LLMs, such as Llama 3, Dubé et al. 2024, Mistral, Jiang et al. 2023, Almo, Groneveld et al. 2024, and DeepSeek, R1, DeepSeek AI et al. 2025, now exhibit remarkable reasoning and in-context learning capabilities. These improvements result from scaling both the models and the web-scraped text datasets they are trained on, as well as from innovations in architecture and optimization techniques. However, while decoders have continuously evolved, encoders have not seen the same level of progress. Worse, their knowledge has become increasingly outdated despite remaining critical for a wide range of downstream NLP tasks that depend on their embeddings, notably for retrieval-augmented generation, Ram et al. 2023, and toxicity classification, Hartvigsen et al. 2022. Despite being 5 years old, BERT, Devlin et al. 2019, and RoBERTa, Liu et al. 2019, remain widely used, with more than 110 million combined downloads from Hugging Face as of the writing of this paper. Similar to decoders, which undergo multi-stage processes of pre-training, instruction tuning, and alignment, encoders also require successive training phases to perform well on downstream tasks. First, encoders go through self-supervised pre-training on large corpora of text with the masked language modeling objective. By predicting masked or replaced tokens, this stage enables models to learn the structural patterns of language and the semantics of words. However, the pre-training task is disconnected from downstream applications, and models require additional training to achieve strong performance in clustering or retrieval. Thus, a second fine-tuning phase is often achieved through multiple stages of semi-supervised contrastive learning, where models learn to differentiate between positive and negative sentence pairs, refining their embeddings in the latent space. Recently, substantial progress has been made in improving the fine-tuning stage of pre-trained encoders, with models like GT, Li et al. 2023b, GENA embeddings, Sturua et al. 2024, SFR embeddings, Meng et al. 2024, and CD, Morris and Rush 2024, significantly outperforming previous encoders on the MTB leaderboard, a recent and challenging benchmark spanning 7 tasks and 56 datasets. However, all these approaches focus on proposing complex fine-tuning methods and do not address the inherent limitations of their pre-trained backbone models. As a result, there is a dire need for a new generation of BERT-like pre-trained models that incorporate up-to-date knowledge and leverage both architectural and training innovations, forming stronger backbones for these more advanced fine-tuning procedures. In response, we introduce NeoBERT, a next-generation BERT that integrates the latest advancements in architecture, data, and pre-training strategies. The improvements are rigorously validated on GLUE by fully pre-training 10 different models that successively incorporate the modifications. This validation ensures that the improvements benefit encoder architectures and highlights how some design choices drastically affect the model's abilities. Additionally, we design and experimentally validate a two-stage training procedure to increase NeoBERT's maximum context window from 1024 to 4096. To ensure a fair evaluation of NeoBERT against existing baselines and to isolate the impact of fine-tuning procedures, we propose a model-agnostic and systematic fine-tuning strategy with straightforward contrastive learning. All models are fine-tuned using this standardized approach and subsequently evaluated on the MTB benchmark. On MTB, NeoBERT consistently outperforms all competing pre-trained models while being 100 parameters smaller than the typical large-sized encoders. With a context window of 4096 tokens, it processes sequences 8 times longer than RoBERT, Liu et al., 2019, and 2 times longer than NeoBERT, Nussbaum et al., 2024. It is also the fastest encoder of its kind, significantly outperforming modern BERT-base and large in terms of inference speed. Despite its compact 250 parameter size, NeoBERT is trained for over 2T tokens, prioritizing training over scale to maximize accessibility for both academic researchers and industry users without requiring large-scale compute resources. This makes NeoBERT the most extensively trained model among modern encoders, ensuring robust generalization and superior downstream performance. Furthermore, NeoBERT maintains the same hidden size as base models, allowing for seamless plug-and-play adoption without modifications to existing architectures. As the only fully open-source model of its kind, we release the code, data, training scripts, and model checkpoints, reinforcing our commitment to reproducible research. 2. Related work. In 2019, Devlin et al. 2019 introduced BERT, a novel approach to embedding text using bidirectional transformers pre-trained without supervision on large corpora. Shortly after, Liu et al. 2019 improved over BERT's pre-training by removing the next sentence prediction objective and drastically increasing the amount of data, leading to RoBERT. Since then, the primary focus of the community has shifted towards optimizing the fine-tuning phase of these models through contrastive learning, where the model is trained to maximize the similarity between positive text pairs while pushing them apart from negative samples. Among the earliest contrastive learning approaches designed for encoders, SimCSE, Gao et al. 2022 demonstrated that sentence pairs could be easily generated by feeding the same input to the model twice and applying dropout to introduce noise. However, this simple approach was soon outperformed by models like GT, Li et al. 2023b, which introduced more advanced contrastive learning techniques. GT employed a weakly supervised stage that takes advantage of the vast number of successive sentence pairs available in traditional unlabeled datasets, followed by a semi-supervised stage incorporating labeled sentence pairs from high-quality datasets such as NLI, Bowman et al. 2015, and Fever, Thorne et al. 2018. Recently, fine-grained strategies have emerged to better adapt models to both task and context. For instance, GIN embeddings, Sturua et al. 2024, introduced task-specific low-rank adaptation, LoRa, adapters. As of January 2025, CD, Morris and Rush 2024 ranks at the top of the MTB leaderboard for models under 250 parameters thanks to 2 key innovations: grouping samples with related contexts into the same batch and providing contextual embeddings for the entire corpus in response to individual queries. However, pre-training has not seen the same level of effort and thus progress, most likely due to its prohibitively high computational cost. RoBERT, for instance, required a total of 1,024 v100 days for its pre-training. As a result, GT, GNU embeddings, and CD all rely on pre-trained BERT, XLMRO BER Takano et al. 2020, and NeoBERT, Nussbaum et al., 2024, to initialize their respective models. The latter, NeoBERT, represents a recent effort to refine BERT's architecture and pre-training. NeoBERT incorporates architectural improvements such as SWI-GLU and rope, utilizes flash attention, and extends the context length to 2048 tokens. Despite these innovations, NeoBERT still relied on suboptimal choices, as discussed in Section 3. In parallel with the development of NeoBERT, Warner et al., 2024, released ModernBERT with the goal of further refining the pre-training of NeoBERT. Although we share some of the modifications, we make distinct design choices and conduct thorough ablations that ultimately lead to greater performance on MTB. 3. NeoBERT. The following section describes NeoBERT's improvements over BERT and RoBERTa, as well as the recent NeoBERT and ModernBERT models. Since GTE and CDE use BERT and NeoBERT as their pre-trained backbone, they inherit their respective characteristics. Table 1 summarizes the modifications. Table 1. Comparison of model architectures, training data, and pre-training configurations. 3.1 Architecture. The transformer architecture has been refined over the years and has now largely stabilized, with models like Llama 3 being essentially the same as the original Llama. NeoBERT integrates the latest modifications that have, for the most part, become standard. Depth-to-width. The concept of depth efficiency has long been recognized in neural network architectures. In the case of transformers, stacking self-attention layers is so effective that it can quickly saturate the network's capacity. Recognizing this, Levine et al., 2020, provided theoretical and empirical evidence for an optimal depth-to-width ratio in transformers. Their findings suggested that most language models were operating in a depth inefficiency regime, where allocating more parameters to width rather than depth would have improved performance. In contrast, small language models like BERT, RoBERTa, and NeoBERT are instead in a width inefficiency regime. To maximize NeoBERT's parameter efficiency while ensuring it remains a seamless plug-and-play replacement, we retain the original, BERT subscript base, width of 768, and instead increase its depth to achieve this optimal ratio. Positional information transformers inherently lack the ability to distinguish token positions. Early models like BERT and RoBERTa addressed this by adding absolute positional embeddings to the token embeddings before the first transformer block. However, this approach struggles to generalize to longer sequences and requires the positional information to be propagated across layers. To overcome these limitations, Su et al., 2023, proposed rotary position embeddings (ROPE), which integrate relative positional information directly into the self-attention mechanism. ROPE has quickly become the default in modern transformers due to its significant improvements in performance and extrapolation capabilities. NeoBERT, like all newer encoders, integrates ROPE. Nevertheless, degradation still occurs with sequences significantly longer than those seen during training. As a solution, Ping et al. 2023 introduced yet another ROPE extension, YARN, which allows to efficiently fine-tune models on longer contexts. NeoBERT is readily compatible with YARN, making it well-suited for tasks requiring extended context. Layer normalization. Consistent with standard practices in modern transformer architectures, we move the normalization layer inside the residual connections of each feed-forward and attention block, a technique known as pre-layer normalization, pre-LN. Pre-LN improves stability, allows for larger learning rates, and accelerates model convergence, Xiang et al. 2020. While all newer encoder models adopt pre-LN, they typically continue to use the classical layer norm rather than root mean square layer normalization, RMS norm. In NeoBERT, we substitute the classical layer norm with RMS norm, Zhang and Senrich, 2019, which achieves comparable training stability while being slightly less computationally intensive, as it requires one fewer statistic. Activations. BERT and RoBERTa utilize the standard Gaussian error linear unit, GELU activation function. However, Shazir, 2020, demonstrated the benefits of the gated linear unit in transformer architectures. These activation functions have since been adopted in several language models, including the Llama family. Following previous works, NeoBERT incorporates the SWI-GLU activation function, and because it introduces a third weight matrix, we scale the number of hidden units by a factor of 2/3 to keep the number of parameters constant. 3.2 Data. Data has emerged as one of the most critical aspects of pre-training, and datasets with increasing quantity and diversity are frequently released. NeoBERT takes advantage of the latest datasets that have proven to be effective. Dataset BERT and NeoBERT were pre-trained on two carefully curated and high-quality datasets, Wikipedia and Book Corpus, Zhu et al., 2015. Azbivsky et al., 2019, demonstrated that increasing data size can improve downstream performance. Liu et al., 2019, pre-trained Roberta on 10 times more data from Book Corpus, CC News, Open Web Text, and Stories. However, Roberta's pre-training corpus has become small in comparison to modern web-scraped datasets built by filtering and deduplicating common crawl dumps. Following the same trend, we pre-trained NeoBERT on Refined Web, Pinedo et al., 2023, a massive dataset containing 600 B tokens, nearly 18 times larger than Roberta's. Although Refined Web does not have strict high-quality constraints, we believe that exposing the model to such a large and diverse dataset will improve its real-world utility. Sequence length BERT and Roberta were pre-trained on sequences up to 512 tokens, which limits their downstream utility, especially without rope and yarn. NeoBERT increased the maximum length to 2048 and employed dynamic NTK interpolation at inference to scale to 8192. To further broaden NeoBERT's utility, we seek to increase the context length. However, due to the computational cost associated with pre-training, we adopt a two-stage pre-training procedure similar to LLMs like Llama 3. In the first stage, we train the model for 1M steps, 2T tokens, using sequences truncated to a maximum length of 1024 tokens, referring to this version as NeoBERT, subscript 1024. In the second stage, we extend the training for an additional 50K steps, 100 B tokens, increasing the maximum sequence length to 4096 tokens. We refer to this final model as NeoBERT, subscript 4096. To ensure the model encounters longer sequences during this stage, we create two additional subdatasets, Refined Web, subscript 1024+, and Refined Web, subscript 2048+, containing only sequence lengths greater than 1024 and 2048 tokens, respectively, alongside the original Refined Web dataset. Each batch is sampled from Refined Web, subscript 1024+, and Refined Web, subscript 2048+, with probabilities 20%, 40%, and 40%. Since longer sequences tend to represent more complex or academic content, this strategy helps mitigate the distribution shift typically observed when filtering for longer sequences. We explore the benefits of this two-stage training strategy in subsection 5.3. 3.3 Pre-training. Encoder pre-training has received less attention than the data and architecture. However, many improvements made to decoders also apply to encoders. NeoBERT combines encoder-specific modifications with widely accepted decoder improvements. Objective in light of Roberta's findings that dropping the next sentence prediction task does not harm performance, both NeoBERT and NeoBERT were only pre-trained on masked language modeling. Moreover, Wedig et al., 2023, challenged the assumption that the 15% masking rate of BERT and Roberta is universally optimal. Instead, their findings suggest that the optimal masking rate is actually 20% for base models and 40% for large models. Intuitively, a model learns best when the difficulty of its training tasks aligns with its capabilities. Based on their insight, we increase the masking rate to 20%, while NeoBERT exceeds it by opting for 30%. Optimization following standard practice. We use the AtomW optimizer, Lashalov and Hutter, 2019, with the same hyperparameters as Llama 2. Beta subscript 1 is equal to 0.9, beta subscript 2 is equal to 0.95, and epsilon equals 10 to the power minus 8. In preliminary experiments, we also considered SOAP, Vyas et al., 2025, a recent extension of the shampoo optimizer, but it failed to outperform Atom and AtomW and has been omitted from the list of ablations. We employ a linear warm-up for 2,000 steps to reach a peak learning rate of 6 by 10 to the power minus 4, followed by a cosine decay to 10% of the peak learning rate over 90% of the training steps. Once fully decayed, the learning rate remains constant for the last 100K steps at a sequence length of 1,024 and 50K steps at a sequence length of 4,096. We use a weight decay of 0.1 and apply gradient clipping with a maximum norm of 1.0. Scale recent generative models like the Llama family, Tuvrin et al., 2023, Dubé et al., 2024, have demonstrated that language models benefit from being trained on significantly more tokens than was previously standard. Recently, Llama 3.21b was successfully trained on up to 90 tokens without showing signs of saturation. Moreover, encoders are less sample efficient than decoders since they only make predictions for masked tokens. Therefore, it is reasonable to believe that encoders of similar sizes can be trained on an equal or even greater number of tokens without saturating. For NeoBERT's pre-training, we use batch sizes of 2M tokens over 1M steps in the first stage and 50K steps in the second, resulting in a theoretical total of 2.1T tokens. Note that because sequences are padded to the maximum length, this represents a theoretical number of tokens. In terms of tokens, this is comparable to RoBERTa and represents a 2x increase over. Table 2. Modifications between successive ablations. The initial M0 baseline corresponds to a model similar to BERT, while M9 corresponds to NeoBERT. NeoBERT. In terms of training steps, this amounts to a 2x increase over RoBERTa and a 10x increase over NeoBERT. Efficiency. We improve efficiency by parallelizing the model across devices using deep speed, Aminabadi et al., 2022, with the 0, Rajpindari et al., 2020, optimizer, reducing memory usage by eliminating data duplication across GPUs and increasing the batch size. We further optimize the GPU utilization by employing fused operators from the XFormers library to reduce overhead, selecting all dimensions to be multiples of 64 to align with GPU architectures, and removing biases to simplify computations without sacrificing performance. To address the quadratic demands of attention, we integrate flash attention, DAO 2023, which computes exact attention without storing the full matrices. For effective design choices, we conduct a series of ablations in controlled settings to evaluate our improvements to the original BERT architecture. We fully train each model for 1M steps, controlling for the seed and data loader states to ensure successive models are trained with identical setups. These resource-intensive ablations were crucial to confirm our design choices, as they are based on the literature of pre-training decoder models. The baseline model, referred to as M0, is similar to BERT subscript base, but includes pre-layer normalization. Following RoBERTa, M0 also drops the next sentence prediction objective. We introduce modifications iteratively, resulting in a total of 10 different models, as detailed in Table 2. To mitigate computational costs, the ablations are evaluated on the GLUE benchmark with a limited hyperparameter grid search of batch sizes, is an element of 16, 32, and learning rates, is an element of 1e-5, 2e-5, 3e-5. For the final model M10, we extend the grid search, as detailed in Appendix C. Results are in Figure 1. Key performance-enhancing modifications as expected. The two modifications that had the greatest impact on the average GLUE score were related to scale. In M2, replacing Wikitext and book corpus with a significantly larger and more diverse refined web dataset improved the score by plus 3.6%, while increasing the model size from 120M to 250M in M7 led to a plus 2.9% relative improvement. Note that to assess the impact of the depth-to-width ratio, we first scale the number of parameters in M7 to 250M while maintaining. Figure 1. GLUE ablation scores on the development set. All modifications are cumulative except for M3 and M6 in gray, which are not included in the subsequent models. Increasing data size and diversity leads to the highest relative improvement, M2, plus 3.6%, followed by the model size M7, plus 2.9%. Packing the sequences and using the Llama 2 tokenizer caused the largest relative drops, M6, minus 2.9%, M3, minus 2.1%. A similar ratio to BERT subscript base, resulting in 16 layers of dimension 1056. In M8, the ratio is then adjusted to 28 layers of dimension 768. Modifications that were discarded in M3, replacing the Google WordPiece tokenizer with Llama BP results in a minus 2.1% performance decrease. The performance gap observed likely stems from inherent differences between the algorithms, training corpus, and design strategies employed by the two tokenizers. We further discuss this in Appendix B. In M6, we unpad the sequences by concatenating samples of the same batch. While this removes unnecessary computation on padding tokens, packing sequences without accounting for cross-sequence attention results in a relative performance drop of minus 2.8%. Although this modification was discarded from our subsequent ablations, we incorporate methods of unpadding with accurate cross-attention in our released codebase, following Kundu et al. 2024. Modifications retained despite performance trade-offs unexpectedly, using Adam W., Lashalov and Hutter, 2019, and cosine decay, Lashalov and Hutter, 2017, in M4 decreases performance by minus 0.5%. As Adam W. introduces additional regularization with weight decay, we expect that it will become beneficial when extending training by mitigating overfitting. Similarly, increasing the masking ratio from 15% to 20% in M5 decreases performance by minus 0.7%. We hypothesize that increasing the task difficulty initially hinders downstream task performance, but is likely to become advantageous when training larger models on more tokens. Consequently, we retain both modifications despite being unable to verify these hypotheses at scale due to the computational costs. 5 experiments. Selecting appropriate metrics and benchmarks is crucial for properly assessing the downstream performance and utility of language models. Following both early and recent studies, we include the GLUE and MTB benchmarks in our evaluations. 5.1 GLUE. The GLUE benchmark, Wang et al. 2019, is a cornerstone of language modeling evaluations and has played a significant role in the field. Although GLUE is now 6 years old and the community has long recognized its limitations, we report the GLUE score due to its widespread adoption and to facilitate the comparison of NeoBERT with existing encoders. Following standard practices, we fine-tune NeoBERT on the development set of GLUE with a classical hyperparameter search and introduce transfer learning between related tasks. Complete details of the fine-tuning and best hyperparameters are presented in Appendix C. NeoBERT achieves a score of 89%, comparable to previous large models while being 100M to 150M. Parameters smaller. We present the results in Table 3. Table 3. GLUE scores on the development set. Baseline scores were retrieved as follows: BERT from Table 1 of Devlin et al. 2019, Roberta from Table 8 of Liu et al. 2019, DeBarta from Table 3 of He et al. 2023, NeoBERT from Table 2 of Nussbaum et al. 2024, GT from Table 13 of Zhang et al. 2024, and NeoBERT from Table 5 of Warner et al., 2024. 5.2 MTB. Beyond the GLE benchmark, we consider the more recent and challenging MTB benchmark, Muenighoff et al., 2023, which has quickly become a standard for evaluating embedding models. With a wide coverage of 7 tasks and 56 datasets in its English subset. MTB tasks rely on the cosine similarity of embeddings pooled across tokens in a sentence. The most common and straightforward pooling strategy is computing the average of each token's final hidden representation. However, because out-of-the-box encoders are trained with the masked language modeling objective, they provide no guarantee that mean embeddings will produce meaningful representations without further fine-tuning. As a result, models require expensive fine-tuning strategies crafted for MTB to achieve strong scores. For instance, Li et al. 2023b, with multi-stage contrastive learning, GNU-embeddings, Sturua et al. 2024, with task-specific low-rank adaptation, LoRa, adapters, and CDE, Morris and Rush. 2024, with batch clustering and contextual corpus embeddings, all push the limits of the leaderboard in their respective categories. These coupled stages make it challenging to disentangle the respective impacts of pre-training and fine-tuning on the final model's performance. To isolate and fairly evaluate the improvements introduced during pre-training, we implemented an affordable, model-agnostic fine-tuning strategy based on classical contrastive learning. This fine-tuning approach was designed in accordance with established methods in the literature. Its controlled settings ensured that all models were fine-tuned and evaluated under identical conditions. 5.2.1 Unified Contrastive Learning. Method given a dataset of positive pairs, D equals Q subscript I, D subscript I to the power plus, subscript I equals 1 to the power n, a similarity metric, S, a temperature parameter, tau, and a set of negative documents. N subscript Q. For each query, Q, the contrastive loss is defined as. The loss function is the negative logarithm of a normalized exponential similarity score. Negative documents can be either generic samples of the same format or tailored hard negatives, which exhibit a high degree of similarity to the contrasted sample in their original representation. We constructed a dataset of positive query document pairs with optional hard negatives based on open-source datasets previously employed in the literature, Li et al. 2023a, for a total of 9 million documents. In addition to the optional hard negatives, we also leverage in-batch, task homogeneous negatives. In line with prior research, Li et al. 2023a, we employ task-specific instructions and temperature-scaled sampling of the datasets. Complete details about the data, training, and evaluation can be found in Appendix D. Results: we found that training for more than 2,000 steps resulted in minimal performance gains. Table 4 presents the complete MTB English evaluation of all fine-tuned models. Although NeoBERT is 100M, parameters smaller than all large baselines, it is the best model overall with a plus 4.5% relative increase over the second best model, demonstrating the benefits of its architecture, data, and pre-training improvements. Table 4, MTB, V1, scores after 2,000 steps of fine-tuning with our unified contrastive learning. 5.2.2 Contextual document embeddings. While a unified fine-tuning framework enables fair model comparisons, computationally intensive fine-tuning techniques are necessary to achieve top-ranking MTB scores. We apply one such strategy, contextual document embeddings, CDE, Morris and Rush, 2024, to NeoBERT. CDE previously led the MTB leaderboard with NeoBERT, CDE V1, and NeoBERT, CDE V2, for English models under 400M parameters. NeoBERT outperforms both, achieving an average score of 66.60, the highest in its parameter class. See Appendix G for more details on the fine-tuning. Table 5, MTB, V1, scores after fine-tuning with CDE. Asterisk ranks on MTB, V1, for models under 400M parameters as of April 2025. 5.3 Sequence length. Following previous literature, NeoBERT underwent an additional 50K pre-training steps, during which it was exposed to extended sequences of up to 4,096 tokens. To assess the impact of this additional training, we randomly sampled 2,467 long sequences from the English subset of Wikipedia. For each sequence, we independently masked each token at position I and computed its cross-entropy loss, L subscript I. The pseudo-perplexity of the entire sentence is then defined as P equals exp 1 over n sigma I equals 1 n L subscript I. We present the results in Figure 2. Figure 2. Pseudo-perplexity in function of the sequence length for NeoBERT, subscript 1024, left, and NeoBERT, subscript 4096, right. This validates the effectiveness of the final pre-training stage on NeoBERT's ability to model long sequences. Although NeoBERT, subscript 1024, was trained exclusively on sequences of up to 1,024 tokens, it generalizes effectively to context lengths approaching 3,000 tokens. This demonstrates the robustness of rope embeddings to out-of-distribution inputs. Moreover, after an additional 50K training steps with sequences up to 4,096 tokens, NeoBERT 4096 successfully models longer sequences. This approach provides a compute-efficient strategy for extending the model's maximum context window beyond its original length. To further test NeoBERT's generalization capabilities, we extend the context beyond what was seen during training and present results in Appendix E. 5.4 Efficiency. To assess model efficiency, we construct a synthetic dataset consisting of maximum length sequences of sizes 512, 1024, 2048, 4096, 8192. For each sequence length, we scale the batch size from 1 to 512 samples or until encountering out-of-memory errors. Inference is performed for 100 steps on a single A100 GPU, and we report the highest throughput achieved for each model and sequence length. Figure 3 presents the results. Due to their low parameter count and relatively simple architecture, BERT and RoBERTa are the most efficient for sequences up to 512 tokens. However, their use of positional embeddings prevents them from further scaling the context window. For extended sequences, NeoBERT significantly outperforms modern BERT, subscript base, despite having 100M more parameters, achieving a 46.7% speedup on sequences of 4,096 tokens. 6. Discussion. Encoders are compact yet powerful tools for language understanding and representation tasks. They require fewer parameters and significantly lower training costs compared to their decoder counterparts, making them strong alternatives for applications that do not involve text generation. Traditionally, the representational capacity of these models has been assessed through downstream tasks such as classification, in particular through the GLUE benchmark. Figure 3. Model throughput, tokens per second, as a function of sequence length is better. Above 1,024 in sequence length, NeoBERT surpasses modern BERT, subscript base, despite having 100M more parameters. While GLUE has played a pivotal role in guiding model adoption, it includes only 9 sequence classification datasets, 4 of which are entailment tasks. Moreover, its small dataset sizes and occasionally ambiguous labeling make it prone to overfitting, with models long surpassing human performance on the benchmark. Although NeoBERT v3 achieves state-of-the-art performance on GLUE by a significant margin, our fine-tuning experiments reveal its comparatively poor performance on the more recent MTB benchmark. MTB encompasses a broader range of datasets and tasks, but attaining high performance on its leaderboard necessitates carefully crafted fine-tuning strategies with costly training requirements. As more complex fine-tuning strategies emerge, it becomes unclear what the source of score improvements is. Moreover, these strategies are not easily reproducible or accessible, limiting the possibility of fair comparison between pre-trained backbones. This underscores the limitations of current evaluation paradigms and highlights the need for more affordable and standardized frameworks. We advocate for future research to focus on the development of standardized fine-tuning protocols and the exploration of new zero-shot evaluation methodologies to ensure a more comprehensive and unbiased assessment of encoder-only models. 7. Conclusion. We introduced NeoBERT, a state-of-the-art encoder pre-trained from scratch with the latest advancements in language modeling, architecture, and data selection. To ensure rigorous validation, we systematically evaluated every design choice by fully training and benchmarking 10 distinct models in controlled settings. On GLUE, NeoBERT outperforms BERT subscript large and NeoBERT and is comparable with RoBERT subscript large. Despite being 100 M parameters smaller and supporting sequences 8 times longer. To further validate its effectiveness, we conducted a comprehensive evaluation on MTB, carefully isolating the effects of pre-training and fine-tuning to provide a fair comparison against the best open-source embedding models. Under identical fine-tuning conditions, NeoBERT consistently outperforms all baselines. In addition, when fine-tuned with more advanced techniques, NeoBERT ranks at the top of the MTB leaderboard for models under 400 M parameters. With its unparalleled efficiency, optimal depth to width, and plug-and-play compatibility, NeoBERT represents the next generation of encoder models. To foster transparency and collaboration, we release all code, data, model checkpoints, and training scripts, making NeoBERT the only fully open-source model of its kind. Broader impact statement. Despite its improvements, NeoBERT inherits the biases and limitations of its pre-training data. Moreover, the greatest jump in performance stems from the pre-training dataset, and as newer, larger, and more diverse datasets become available, retraining will likely be needed to further improve its performance. Nonetheless, NeoBERT stands today as an affordable state-of-the-art pre-trained encoder with great potential for downstream applications. Acknowledgements. Sarath Chandar is supported by the Canada Safar AI Chairs Program, the Canada Research Chair in Lifelong Machine Learning, and the NSERC Discovery Grant. Quentin Fournier is supported by the Lambda Research Grant Program. The authors acknowledge the computational resources provided by Mila and the Royal Military College of Canada. Training details. NeoBERT was trained on 8H104.1.050 000 steps for a total of 6,000 GPU hours. In the first stage of training, we used a local batch size of 32, 8 gradient accumulation steps, and a maximum sequence length of 1,024 for a total batch size of 2M tokens. In the second stage of training, we keep the theoretical batch size constant and increase the maximum sequence length to 4,096. The ablations. B1 baseline. Our first model, M0, is modeled after BERT subscript base in terms of architecture. The only two differences are the absence of the next sentence prediction objective, as well as pre-layer normalization. Each successive model, up until M8, is identical to the previous one on every point except for the change reported in Table 2. B2 tokenizers. We refer to the Llama WordPiece tokenizer as LlamaTalk and the BERT VP tokenizer as BERTtalk. Under identical conditions between ablations M2 and M3, the use of LlamaTalk over BERTtalk decreases the GLUE score by a relative drop of 2.9%. Although further investigation would be required to analyze this drop, we highlight several key differences between the two tokenizers. While LlamaTalk uses byte pair encoding, BP, BERTtalk relies on the more expressive WordPiece algorithm, which better models token likelihoods in text. Moreover, their training data largely differs. LlamaTalk was trained on a dataset mostly composed of the Common Crawl, whereas BERTtalk used the higher quality book corpus and Wikitext datasets. Finally, LlamaTalk is cased and handles unknown UTF, 8 characters at the byte level, while BERTtalk is uncased and character level. This leads LlamaTalk to include redundant tokens, e.g., the and rare byte sequences, limiting space for more frequent tokens under a finite capacity. See GLUE. We perform a classical parameter search with learning rates in 5e-6, 6e-6, 1e-5, 2e-5, 3e-5, batch sizes in 4, 8, 16, 32, and weight decay in 1e-2, 1e-5. In addition, we start training from the best MNLI checkpoint for RTE, STS, MRPC, and QNLI. We fine-tune on the training splits of every glue dataset for 10 epochs, with evaluation on the validation splits every n steps n, being defined as min 500 len dataloader //10, with early stopping after 15 evaluation cycles if scores have not improved. Following BERT, we exclude WNLI from our evaluation to the power 3. For tasks with 2 scores and for MNLI matched and mismatched, we report the average between the two metrics. DMTB. D1 Evaluation of pre-trained models. As demonstrated in Figure 4, evaluating out-of-the-box pre-trained models on MTB is inconclusive. In that setting, BERT subscript base outperforms both BERT subscript large and RoBERTa subscript large, highlighting the importance of fine-tuning to ensure representative evaluation on the MTB benchmark. D2 Contrastive learning. Following the existing literature, we designed a simple fine-tuning strategy entirely agnostic to the models evaluated. We used cosine similarity and tau equals 0.07 as a temperature parameter in the contrastive learning. Table 6. Optimal hyperparameters for GLE tasks. The grid search was conducted over batch sizes 2, 4, 8, 16, 32, learning rates 5e-6, 6e-6, 8e-6, 1e-5, 2e-5, 3e-5, and weight decay values 1e-2, 1e-5. Figure 4. Zero-shot evaluation of BERT and RoBERTa on the English subset of MTB. Loss. Additionally, we sampled datasets with a multinomial distribution based on their sizes and subscript j equals 1 to the power m, with alpha equals 0.5. Pi equals a term raised to alpha, divided by the sum of similar terms raised to alpha. We trained on the following fully open datasets: AG News, Zhang et al., 2016, NLI, Bowman et al., 2015. Williams et al., 2018, Amazon QA, Gupta et al., 2019, Concurrent QA, Aurora et al., 2022, GitHub. Issues: Lee and Lee, 2023, GUIQ, Kashabi et al., 2021, MedMCQA, Pal et al., 2022, NPR4, PubMed QA, Jean et al., 2019, Sentence Compression, Filipova and Alton. 2013, Stack Exchange to the power 5, Trivia QA, Han et al., 2019, WikiHow, Kupi and Wang, 2018, Yahoo Answers, Zhang et al., 2016, as well as the available training splits of MTB datasets, Stack Overflowed Up Question, Fever, Thorne et al., 2018, MS Marco, Bajaj et al., 2018, STS-12 and STS Benchmark, Sarah et al., 2017. We fine-tune every model for 2,000 steps and evaluate on MTB in Float 16. The complete results are presented in Table 4. Figure 5. Average MTB scores of fine-tuned encoders grouped by task type. The average score is computed across the 56 tasks of MTB English. NeoBERT is the best model on 5 out of 7 task types and the best model overall. See Table 4 for complete scores. D3 Task Instructions. We provide the set of instructions used for fine-tuning in Table 7 and evaluation in Table 8 and Table 9. Table 7. Instructions for fine-tuning on the different contrastive learning datasets. Table 8. Instructions for evaluation on the different MTB tasks. Table 9. Instructions for evaluation on the different MTB tasks. Context length. We compute the pseudo-perplexity on sequences sampled from English Wikipedia. Although NeoBERT has only been exposed to sequences up to 4,096 tokens during training, it correctly models sequences up to 6,000 tokens. Additional training or rope extension techniques such as yarn, Peng et al. 2023, would be needed to further extend the context window. Figure 6. Pseudo-perplexity in function of the sequence length for NeoBERT, subscript 4096, for extension beyond sequence length seen in training. NeoBERT generalizes natively for sequences under 6,000 tokens. F efficiency. Table 10 presents the complete results of model efficiency evaluations. Table 10, throughput, 10 to the power 3, tokens/second, in function of the sequence length, with optimal batch size. G. Contextual document embeddings. One popular application for BERT-style models is to generate embedding vectors for use in tasks such as classification, clustering, and retrieval. State-of-the-art embedding models below 400 M parameters are trained using contextual embedding techniques, Morris and Rush, 2024. The highest-performing similar-sized embedding models were trained with backbones initialized with NeoBERT, Nussbaum et al., 2024, and more recently ModernBERT, Warner et al., 2024. In this section, we question whether contextual document embeddings (CDE) might perform better when initialized from NeoBERT. G1 method. We train our embedding models using both the contextual batching strategy and contextual architecture described in Morris and Rush, 2024. Contextual batching. To train a contextual embedding model, we have to first group documents from a larger corpus into miniature pseudo-contexts, which comprise the batches for training. We do so by minimizing the following batch clustering objective. Minimize the sum of costs for each block, where each cost is a function of a data query pair and a centroid. Here, B subscript 1. B to the power B represent the orderings of batches of training data, and C to the power asterisk operator are the corresponding centroids. M, D, Q indicates the distance, typically Euclidean, between embeddings of document, D, and query, Q, from batch, B to the power B. We can approximate this efficiently using a modified k-means solver. We follow the same procedure as Morris and Rush, 2024, to cluster documents for each training set. Contextual architecture. Contextual embedding models in effect use two model backbones, one to embed similar documents in context and another to embed documents conditioned on contextual information. We can express contextual embedding vector, phi, using both models, M subscript 1 and M subscript 2. Phi of x given D is M2 applied to M1 of D1 through Dj and E of x1 through xt, where x is a document or query comprised of tokens, x subscript 1, x subscript t, and D is a set of documents from the surrounding context. We train phi end-to-end by backpropagating through both M subscript 1 and M subscript 2, using the custom two-stage gradient caching procedure described in Morris and Rush, 2024. G2 data and hyperparameters. Training stages and data. We train our models in two stages. The first stage is a large, noisy, contrastive pre-training stage with 235 M query-to-document pairs per epoch. The second is a short fine-tuning step on 1.5 M high-quality data points. We train each stage for 3 epochs with the Atom Optimizer with 1,000 steps of warm-up to a learning rate of 5e-5 and linear decay to 0 throughout training. Instead of mining hard negatives, we cluster the datasets for contextual batching. We embed for clustering and filter hard negatives within a batch using GTE Large, Li et al., 2023a. We set both the batch size and cluster size to 512. Unlike many contrastive training setups, we neglect to share negatives between GPUs. We evaluate our contextual embedding models on the 56 tasks of the English version of MTB, Muenighoff et al., 2023. To maintain consistency with prior iterations of CDE, we train these models with 512 in-context documents and a per-document sequence length of 512. This produces a second-stage input size of 1024 tokens. G3 results. Our contextual embedding results are detailed in Table 5, averaged across tasks in MTB. With a score of 66.60, NeoBERT significantly outperforms ModernBERT in embedding-related tasks. In our case, the gap between NeoBERT and ModernBERT, about 1 mdb point, is notably larger than the gap between ModernBERT and NeoBERT, approximately 0.6. NeoBERT's largest improvements are shown in retrieval, re-ranking, clustering, and classification tasks. We see a small drop in performance in STS compared to ModernBERT, which we hypothesize may relate to the mix of pre-training data. When compared to other models in MTB, NeoBERT fine-tuned with CDE is state-of-the-art in its parameter class, outperforming all other similar-sized embedding models as of April 2025, such as GTE with 64.36, Li et al. 2023a, BGE with 63.99, Chen et al. 2024, and GIST with 64.13, Solitorio, 2024. To the power 1, https://huggingface.co/chandar-lab/NeoBERT. To the power 2, https://github.com/chandar-lab/NeoBERT. To the power 3, C12 in https://gluebenchmark.com/FAQ. To the power 4, https://huggingface.co/datasets/sentence-transformers/NPR. To the power 5, https://huggingface.co/datasets/sentence-transformers/stackexchange-duplicates.